Imagine a world painted in green and coal black, a planet where forests tower like living skyscrapers, where dragonfly wings blot out the sun for a fleeting breath, and where the very air itself grows richer, heavier with oxygen than what you breathe today. This is the Carboniferous, a 60 million year chapter in Earth's long story that begins about 359 million years ago and closes around 299 million years ago. It is a period whose name hints at its legacy, coal bearing. But the Carboniferous is more than coal. It is an era of invention, of new ways to live on land, of massive shifts in climate and continents, of booming life both above and below the waves. It is in many ways the planet getting its breath, literally and figuratively, readying for the future. Picture the continents. Not the familiar shapes on a modern globe, but tectonic giants wandering and bumping, assembling the supercontinent Pangaea. Gondwana stretches over the South Pole, wrapped in ice at times. Laurussia drifts across the equator, bathed in tropical light. Between them, oceans like the Reich and the Paleotethys carve their channels, influence ocean currents, and dictate who lives where. As continents collide and squeeze, mountain chains rise, the central Pangean mountains forming, the Urals stitching together. And in these pushing and grinding processes, the stage is set for climate change that will ripple through ecosystems worldwide. Now zoom in on the wetlands of the tropics, low-lying basins where water lingers and decays, where trunks of towering lycopsid trees, relatives of tiny modern club mosses but scaled up to mammoth proportions, march into the sky. Their bark-like skin, their ladder-like leaves, and the vast mats of roots known as stigmarian networks anchor these giants in humid soils. Next to them, tree ferns unfurl feathery crowns, calamites, ancestors of horsetails, stand like bamboo colossuses, and chordates stretch strap-like leaves toward the sun. These aren't just plants, they are the architects of a new kind of landscape, peat-forming, oxygen-increasing, coal-making forests, the steam of decay and preservation. In these oxygen-poor, waterlogged peat mires, plant matter accumulates faster than it decays. Layers upon layer of organic debris pile up, and over millions of years of burial, compression, and heat, peat becomes coal. This deep, dark transformation is why the Carboniferous left such a mark in rocks around the world. Great coal seams, the fuel of human revolutions far later, are the fossilized echoes of these ancient swamp forests. But why did so much coal form now, more than in almost any other period? Two bold ideas offer answers. One says, the fungi that could eat lignin, the tough stuff in wood, had not yet evolved fully, so woody debris piled up. The other argues, the perfect combination of geography, climate, and low-lying basins created an unparalleled environment for peat accumulation. Perhaps truth sits somewhere between them, shaded and layered like the coal itself. Beneath the waterline, life is no less spectacular. Shallow epicontinental seas spread across continental shelves, hosting reef communities of sponges and corals that build in aragonite-dominated waters. Crinoids, those stalked sea lilies, create dense underwater forests whose skeletons form limestone beds. Brachiopods, bryozoans, and diverse foraminifera thrive, their shells a testament to a world that, while different, is already richly populated. But the sea is not static. Changes in seafloor spreading, mountain building, and climate alter seawater chemistry. Aragonite seas replace calcite seas as magnesium to calcium ratios shift, favoring organisms that build aragonite shells. Isotopes of strontium, carbon, and oxygen dance through rocks, telling geochemists about weathering mountains, glacial episodes, and the great drawdown of atmospheric CO2. The Carboniferous climate is dominated by an epic chill, the late Paleozoic Ice Age. This icehouse stretches from the late Devonian into the Permian, with glaciers waxing and waning across southern Gondwana. Sea levels fall and rise in rhythmic pulses, and the continental shelves record this with stacked sediments called cyclothems, repeating sequences of freshwater, swamp, delta, and marine layers. These patterns were driven by ice growth and melt, sometimes paced by 100,000-year Milankovitch cycles. Because the shelves were so flat, small sea level changes created enormous shifts in shoreline position. When ice grew, sea levels dropped, rivers cut channels across exposed shelves, and erosion stripped earlier deposits. When ice melted, seas transgressed, peat swamps drowned and were buried, marine limestones spread. The result is a record of repetition, rhythm in stone. and life responded. The Carboniferous sees an explosion of insects, arachnids, and myriapods on land. The air itself, enriched at times to levels far above today's 21% oxygen, may have played a role. Models and fossil clues suggest oxygen rose from low 20s to perhaps as high as 25 to 30% during parts of the period. In such oxygen-rich air, breathing becomes less limiting for arthropods, and some grow to astonishing sizes, dragonfly-like predators with wingspans near 3 feet, millipede-like Arthropleura stretching over 2 meters. Giant scorpions patrol swampy margins, colossal insects patrol the canopy. It is a world where exoskeletons and simple respiratory systems find fewer constraints and can test new sizes and lifestyles. Vertebrates, too, are rewriting their rulebook. From the Devonians' piscine ancestors arise limbed, four-footed creatures, stegocephalians and early tetrapods that push farther onto land during the Carboniferous. Amphibian lineages diversify into new forms. Some become river hunters, others small terrestrial predators, some long and eel-like, others squat and armored. For a time, amphibians dominate land vertebrate niches. But the Carboniferous also witnesses the first real steps toward full independence from water. The emergence of amniotes, tetrapods that lay eggs with protective membranes, the amniote egg, and develop scaly, keratinized skin. These innovations let early reptiles and synapsids explore drier habitats. Hylonomus, a small lizard-like sauropsid, and Archaeothyrus, an early synapsid, appear in rock-sheltered fossil sites, hinting at the lineage that will later give rise to reptiles and mammals. Yet this flourishing is not uninterrupted. The period's middle and later chapters bring climatic tightening, cooling, glaciations, and the Carboniferous rainforest collapse. Once extensive equatorial rainforests fragment as climates become cooler and drier. Swamp forests collapse into isolated patches, and biotic communities shift. Amphibians, tied to moist environments for reproduction, suffer declines in diversity and range. Amniotes, with terrestrial eggs and water-conserving skins, gain an ecological edge and diversify into new roles. The Carboniferous rainforest collapse is less an instant catastrophe and more a major reworking. Some lineages falter, others adapt, and the tapestry of life changes its weave. Beneath these biological dramas lie chemical and isotopic stories. Carbon isotopes record pulses of organic burial and release, marking times when vast amounts of carbon were sequestered in sediments and when the system rebalanced. Oxygen isotopes in marine fossils climb and fall with glacial pulses. Strontium ratios shift as mountain ranges are uplifted and weathered, pouring radiogenic elements into the sea. In essence, rocks and shells are a ledger of Earth's bookkeeping, noting when continents rose, when forests expanded, and when ice locked away ocean water. The Carboniferous is also an age of tectonic theatrics. The Veriscan, Alleghanian, and Ouachita orogenies crumple continents and stitch terrains together across what will become Europe, North America, and beyond. The Uralian orogeny closes ancient ocean basins, welding Kazakhstania to Laurussia and producing the backbone of the Urals. Smaller terrains, bits of crust that once drifted as islands and microcontinents, collide, accrete, and fold. These collisions drive erosion, change river systems, and intensify weathering, one of the levers that help draw down CO2 and drive climate cooling. But the Carboniferous is not only about slow geological change. There are bursts and gaps that puzzle paleontologists. Romer's Gap, for instance, marks the earliest Carboniferous interval with few terrestrial fossils. For decades, it seemed like a blank page in vertebrate evolution. Recent work hints that a global dip in atmospheric oxygen and ecological upheaval contributed to this sparse record, a reminder that the fossil record is both a window and a mirror, showing what was abundant and what was transient. The seas, meanwhile, tell their own stories of extinction and radiation. While some groups dwindle, trilobites continuing their long decline, others radiate. Foraminifera diversity booms. Crinoid thickets flourish and then ebb. Cephalopods change form. Nautiloids persist. Ammonoid relatives experiment with coiling and ornament. The marine world is resilient and dynamic, responding to the changing chemistry, sea levels, and nutrient flows driven by continents and climate. Return once more to the great coal forests under a crimson sunset. Fire, too, makes an appearance. Charcoalified layers in rocks tell of wildfires, and their presence is paradoxical. Fire needs oxygen, The prevalence of charcoal suggests oxygen was elevated enough at times to sustain widespread burning. Fires cleared patches, reshaped communities, and fed cycles of regeneration. They remind us that life and its environment are always in feedback. Plants sequester carbon and raise oxygen. Oxygen fuels fires that prune the landscape. Fires alter habitats, favoring some species over others. As the Carboniferous draws to a close, the world is transformed. Continental collisions press on, ice reaches episodic peaks, forests rearrange, and new vertebrate lineages, dryland amniotes, lay the foundation for later dominance. The atmosphere's composition has shifted, seas have cycled through chemistry and level, and the rocks have stored stories in coal seams and limestones. The legacy of this period is not only geological fuel or museum specimens, but the very rearrangement of ecosystems that set the stage for the Permian and eventually the age of dinosaurs and mammals. To step out from this narrative and reflect, the Carboniferous is a study in extremes and transitions. It is a time when life pushed boundaries, lifting off the water, building towering forests, taking the air in great gusts to power oversized wings. It is a moment when Earth's systems, tectonics, climate, chemistry, and life engaged in a dynamic dance, each step changing the next. In the layers of rock beneath our feet, we find the echoes, coal seams that once burned in ancient swamps, stone forests of crinoids, and fossilized wings that whisper of gargantuan insects. There is also an ancient lesson in the Carboniferous that resonates now. Ecosystems and atmospheres are tightly coupled. The growth of forests pulled carbon from the air, altering climate and oxygen levels, which in turn reshaped life. Today, as humans alter carbon cycles, the Carboniferous reminds us how biology and geology can rewrite planetary conditions over deep time. It is a humbling story and an inspiring one, a testament to life's creativity, Earth's capacity for change, and the complex interplay that shapes the world.